Hello, my name is Mike Beeler with the Power Delivery Intelligence Initiative. Welcome to today's webinar sponsored by PDI Squared and Borealis. This webinar is about the 21st century costs of undergrounding. Those costs are coming down. We wrote an article about it back in March of this year, talking about the costs of undergrounding in material science and design and construction and operations and maintenance, and how those costs are compared to the cost of overhead transmission and distribution. And our premise is that those costs are coming down, and we want to talk about that today. This is the fifth in a series of 6 webinars to talk about that very thing. And today we're with David Lindsay of the Borealis Group. And David is going to explain what Borealis is doing with regard to material science that I think you're going to be fascinated by. So David Lindsay, say hello to our audience, give a little bit of your background and a little bit of introduction to the audience. Thank you.
Hey, hello everybody. Good afternoon. This is David Lindsay. I'm marketing manager for the energy division of Borealis Group for North America. I'm located in Charlotte, North Carolina. I've been in the wire and cable business for about 25 years now. Have worked for cable manufacturers as well as electrical contractors doing installation and field work for underground power systems. And I'll be discussing Borealis technology for cost-effective transmission and distribution cable today.
Okay, thank you, David. Appreciate that. Again, PDI Squared, the Power Delivery Intelligence Initiative, is a sponsor with Borealis of this webinar. And PDI Squared is basically a group of companies that you already know, contractors, consultants, cable manufacturers, and people that are interested, companies that are interested in advocating for underground transmission and distribution. We want to make sure that underground gets a good look by planners and engineers as they're starting to evaluate how we're going to build out the transmission and distribution system of the future. So I'm going to pass it back to David and ask him to go ahead and talk about what his agenda is for today. He'll talk for about 35 or 40 minutes about what Borealis has planned, and then we'll take the last 15 or 20 minutes and take your questions. So if you have any questions, feel free to send them on in. But David, I'm going to send it right back to you and tell us what your agenda is for today.
Great, thanks, Mike. So I'll give a brief introduction to who Borealis is, the material and the technology that we're bringing to market in the realm of underground cable. We're going to talk about cost-effective material science and solutions for not just distribution cable, but high voltage and extra high voltage transmission cable, as well as some newer technology for HVDC and what we're doing in the offshore wind space, particularly in Europe, but this is becoming a bigger and bigger topic here in the U.S. I think everybody's aware of the emerging market, especially off the East Coast right now in offshore wind here in the U.S. So we'll talk a little bit about that at the end, but we'll focus mainly on underground technology, underground cable in the transmission and distribution space. So Borealis, if you're not familiar with Borealis, we are a specialty polymers company headquartered in Europe, but we have a footprint here in the United States that I'll show you in just a second. We make both polyethylene and polypropylene for a lot of different industries and applications, one of which is what we call our energy business. And this is wire and cable, distribution, transmission, underground cable, as well as things like building wire, automotive wiring harnesses, low voltage cables, fiber optics, all different varieties of wire and cable. We're about.
So David, I look at this, David, and you talk about polyolefins. What's a polyolefin? I mean, you've explained it to me. Explain that to our audience, if you would, please.
Sure. So polyolefins is a generic term that covers a kind of a broad family of polymers. Which include polyethylene, which we'll be talking mainly about today, as well as polypropylene, which are the two main polymers that Borealis makes, polyethylene and polypropylene, both of which are used in wire and cable. But for the discussion today, for medium and high voltage underground power cable, polyethylene is the material we're really talking about. But we do manufacture and offer polypropylene materials. There are polypropylene jackets for cables. we have some polypropylene products in the fiber optic space, that type of thing. But we'll be focusing on the cross-linked polyethylene today. Yeah.
Okay. Thanks.
So Borealis' global footprint, like I mentioned, headquartered in Europe. We've got a lot of manufacturing locations scattered across Europe, but we do have a U.S. footprint. We've got 3 manufacturing facilities in the U.S. as well as sales and support offices in the U.S. and Mexico. We're about an $8 billion company in terms of annual sales, about 7,000 employees, so a pretty sizable organization with a global footprint to support not just wire and cable, but a lot of other industries as well.
So, David, let me ask you a question. We know that Pacific Gas and Electric just made a huge announcement about undergrounding about 10% of their system. It's for fire mitigation. Basically, the CEO has come out and said it's too expensive not to do it in talking about underground. So they put out a press release to say they're going to spend $15 to $30 billion on undergrounding about 10% of their transmission and distribution system. Fascinating for the industry. I think many others will follow, especially in California, with regard to fire mitigation. And of course, we see some movement on the East Coast and specifically in the Southeast with strategic undergrounding programs. So as more utilities make a decision to put their assets underground, whether they're existing assets or even new construction, as you'll probably talk about with renewables and renewable developers, how is Borealis going to be ready to do this? I think one of the big challenges for our industry is having the personnel and the equipment and the material ready to respond to a market that is going to likely really take off here in the years to come. How is Borealis going to be prepared for that?
Yeah, that's a great question and a great point. We're really excited about the announcement that came out of California last week. I think everybody on this call probably is, as we're all in this market. So that's a huge amount of cable that they're talking about, a huge investment, and certainly a good question that you're bringing up. So our U.S. footprint includes the existing site in New Jersey that makes medium and high voltage cable insulation and shielding materials that we're going to talk about. But in addition to that, we're currently under construction in Texas for a greenfield plant, a new cracker, as well as a new polyethylene reactor unit. You can see the numbers there. It's 625,000 metric tons per year of new polyethylene capacity. Part of that capacity will support the wire and cable industry. So we'll have some jacket grade material that comes off of that plant in Texas that is specifically designed for things like medium voltage underground cable, the black jacket that's on the outside of the cable. In addition to that, some of the other products that will come out of that plant will support things like HDPE pipe, conduit that would be in the ground that the cable would be installed into. So there's big investments being made right now by Borealis to support growth in this space. I know other members of the value chain are looking at expansions or have expansions underway. So I think as an industry, we've kind of been reading the tea leaves that this market is growing. There's been strong growth for the last 5 to 10 years in underground cable. And I think everybody sees that that's going to continue for a while. And announcements like what we saw last week from PG&E is just more of the same, really, for market growth that we've seen over the last 5 years. So different types of products that we make for wire and cable, both from the high and extra high voltage transmission cables all the way down to twisted pair data cable, fiber optics, low voltage signaling cables, even capacitor film is what we include in our energy product mix. But today we're going to be focusing on medium and high voltage cable, as I've mentioned before. So from a grid perspective, high voltage cables get used primarily in the transmission system connections from generation to substations or between substations Primarily in big cities is where we've seen the majority of underground transmission cable installed in this country. When you get into dense urban areas, it's very difficult to site overhead transmission lines, and that's typically where you see the high voltage, extra high voltage cables being installed. There are exceptions to that in some suburban areas, places that you wouldn't call dense urban downtown cities. But most of the underground transmission cable today is in a dense urban underground type of area.
And David, how do you like to define high voltage transmission? Would you say that's like 115 kV class and above?
Yeah, so a good question. Generally, as a rule of thumb, we consider high voltage 69 kV through 138 kV, and then extra high voltage 230 kV and above.
Okay.
And then medium voltage would be 15 through 46 kV. And generally, the industry standards and some of the requirements, testing requirements, follow those general voltage classifications as well.
Okay, good. Thank you. You talk about industry standards and such. I am going to ask you at some point in time, and maybe you have a slide on it, about the specifications, like industry specifications that an engineer would want to look at if they're trying to say, okay, I want to put a better material into my cable spec. Where do I look for those specs? Do I go to the ICC, the Insulated Conductor and Cable Committee of the IEEE, or AEIC, or what? And you may be talking about this later, but
yeah, I've got a slide coming up. I do have a slide coming up that addresses some of the industry standards, and we can address that question when we get there. Remind me if I don't bring it up, but
okay,
we will get to that in a second.
Great.
Absolutely. Yeah. So high voltage cables, and then distribution cable or medium voltage cable at 15 through 46 kV in the U.S. So these are the different cables that we'll be talking about today. I will add too that in the transmission space, we will include HVDC. There's quite a bit of HVDC that's been installed around the world, not so much in the U.S. yet. Hopefully that will change, and we'll talk about that towards the end of the hour. So what do we see as drivers in the industry? Why is undergrounding a hot topic today? We mentioned PG&E, fire prevention, wildfire mitigation, but we're seeing a lot of undergrounding, especially in the distribution part of the system, around grid hardening and resiliency programs. If you've been following this series of webinars that PDI Squared is hosting, we've talked a lot about hardening and resiliency. We've talked about some of the programs that are ongoing at different utilities along the East Coast, Dominion in Virginia, as well as some others. So that's one of the new big drivers for growth in the distribution cable space, is hardening and resiliency in terms of severe weather events. Growth in renewables is another big driver. There's a lot of wind farm development that's happened over the last few years, and the collection system for onshore wind farm is 35 kV underground medium voltage cable. So there's been a big push and big growth in the cable industry simply because of the amount of wind and solar that's being installed. Utility scale wind and solar requires medium voltage underground cable as part of the collection system. And then we're seeing also a lot of investment in transmission systems, and we hope that this will continue, and I think it needs to continue and grow. In fact, as cities grow and the economy continues to grow as it has in the last few years, we need more and more reliable power. Everybody's working from home. We have to keep the lights on at everybody's house. And so a more resilient and robust infrastructure is part of that equation. We're seeing a lot of long distance transmission needing to go in to support renewable connections. Particularly in Europe, we're seeing a lot of that long distance transmission be underground cable. And I think we're starting to see signs that may happen in the U.S. as well.
So, David, you don't necessarily, at Borealis Group, you're not selling to EPC contractors or to renewable developers or to utilities. You're selling your polyethylene raw product to cable manufacturers that in turn are selling to that aforementioned group. Is that correct?
That is exactly correct. Yes, Mike.
Okay. So
yeah, so we make.
So if I went to the IEEE general meeting or the big IEEE shows or to the ICC committees and things like that, I wouldn't necessarily see Borealis Group there, but I would see cable manufacturers that use Borealis product, basically.
Well, we are there. You would absolutely see Borealis at the ICC, IEEE, CGRAE, GCOBL, the usual list of cable-related industry technical meetings, because we're there discussing and talking about our materials, our new materials, things that we're working on, and what we're offering to the industry to help improve cable life, cable reliability, that type of thing. And with regards to industry standards, you had asked this question before. These standards that are on here and the specifications that are on this slide are medium voltage. So this is all distribution cable related. There's a similar list of standards and specifications for underground transmission cable, but these are specifically for distribution. So the standards at the top, primarily the ICEA standards, lay out technical requirements on how a cable is built, what materials can be used, performance of those materials, testing, aging tests, that type of thing. And one of the key parameters in underground distribution cable is wet aging, wet electrical aging, and a test that we call the Accelerated Water Treating Test, or AWTT. And what this is a 1-year wet aging test at elevated voltage. And then when it's done, you do not only electrical breakdown, but other forms of evaluation on that cable. And over the years, as materials have gotten better and cleaner, cable manufacturing processes have gotten better and cleaner, the performance of these materials in terms of their breakdown voltage has continued to steadily go up and up and up and up. You can see the horizontal black bars on this chart represent the minimum performance requirements that are laid out in these standards and specifications. And today's materials more than double the minimum requirements. And this is true in a lot of other parameters in the cable performance as well. But both the unaged initial breakdowns as well as the 360-day wet aging breakdown performance far exceeds minimum requirements in the standards. The blue bar, what we call a conventional conductor shield, again, more than double the minimum requirements. And then the orange bar, or what we refer to as super smooth conductor shield materials, and this is the inner semicon that touches the copper or aluminum conductor and separates it from the actual insulation material, smooths the electrical stresses in the cable. So the super smooth version of that, again, much higher performance. And in fact, the super smooth materials that some people specify in their medium voltage cable are really designed and intended for extra high voltage cables. So you're taking a material that's designed to be used on, say, a 345 kV underground transmission cable, and they're applying it on a 15 kV distribution cable. So as you would expect, the performance is much, much better, right? You get a much better result with a 345 kV type of material than you would from a 15 kV type of material. But the flip side of that is it costs substantially more, as you would expect. And so as we get into discussions with our customers and the end users at utilities and other end users of underground cable, there are discussions that can be had around what's the most cost-effective way to get the performance that you really need. And this is one of the choices and one of the parameters that's out there that can be looked at in terms of cost-effective undergrounding. Do you really need to use an EHV grade semiconducting material in a 15 kV cable?
Right. And so that is a great point, David. And I think that the message here is that cables are performing better than ever before. And when you talk about performance, really what you're talking about is longevity. These cables are lasting, 40, 50, 60 years of life, if they're run properly and they're not, overheated. And that it's imperative that an engineer, like a standards engineer, really evaluate some of these specifications and determine, what kind of material is going to go in, and are they going to have a 345 kV standard when a 15 kV standard really is going to work. And then it's also important for planners to understand that, hey, I can get a lot of life, I can get a lot of longevity out of these better performing cables. Is that a good takeaway from this slide, or is there more?
Yeah, absolutely. No, that's exactly the key point here, is that cable performance, cable materials have gotten much, much better over the years. The cable extrusion manufacturing processes have gotten much, much better. And so 15, 20 years ago, maybe it was worthwhile to specify super smooth conductor shields on a 15 or 25 kV cable. But with today's technology, I think it's something that can be reevaluated.
Great. Thank you for explaining that.
So if we now shift gears and talk a little bit about transmission, the critical parameter in transmission cable materials is cleanliness. And that's not just physical cleanliness in terms of impurities, contaminants, foreign particles that may be introduced somewhere along the way, but it's also chemical cleanliness. And that's where having high quality materials from a supplier like Borealis is extremely important. We have extremely tight tolerances internally on both physical as well as chemical cleanliness of the insulation and the semiconducting materials. And the higher and higher you go in voltage, the more critically important these parameters become. The little graph that you can see on the left-hand side of the slide here is plotting inner and outer electrical stress on the cable. So the electrical stress at the conductor, and then on the outside of the insulation in terms of kV per millimeter. And so you can see that today's EHV cables, we're talking 345, 500 kV cables, you're in the 14, 15, even 16 kV per millimeter range for what's installed and in service today. And so as these stresses have gone up and up and up over the years, as we've gone to higher and higher voltage cables and thinner insulation walls, this cleanliness has become more and more important. And that holds true all the way from when Borealis is making the pellets and packaging the pellets to when they get shipped to the cable manufacturer and how they handle them and use them to make a cable. And so those processes have gotten better and better and better over the years. And just to try and kind of put it in perspective, if you look at the graphic on the right, 1 teaspoon worth of what we call contaminants at our maximum allowable particle size, which is about 100 microns. If you evenly distribute that in a high voltage cable, you're going to ruin over 1,500 miles worth of cable in an EHV cable. So it doesn't take very much in the way of contaminants or impurities introduced into the system to render the cable useless, because it will lead to breakdown.
That's interesting, and that actually aligns with a question that just came in from somebody in the audience. And they said, what are the factors, David, that determine the design life of a high voltage cross-linked polyethylene cable? So this is the contaminants, obviously, is one of them. Are there other factors that you guys take a look at as well?
Well, there's a number of different factors. From a materials supplier standpoint, cleanliness of the material is the biggest factor that we have control over. Making sure that, as I mentioned, both physically and chemically, the insulation and the semiconducting shields meet and exceed the performance specifications and requirements that are set out. But then we hand the ball, if you want to use that cliche, we hand the ball to the cable manufacturer, and they then use those materials to manufacture the cable. And there's a whole host of parameters in the cable manufacturing processes that directly impact that as well. Making sure things are clean, making sure the cables are round, that the different layers of the cable are concentric with each other. So there's a whole host of things that need to be looked at very carefully to ensure longevity of the cable.
Great, thank you.
So transmission cable, one of the things that I'll point out again on this chart on the left, and we'll come back and talk about it a little bit later, is this overlap we see in the electrical stresses between medium and high voltage cables. Particularly in the US, our medium voltage cables are what we call a wet design, in that there's no metallic moisture barrier. You have no metallic layer in the cable to keep moisture out. You put the cable in the ground, it's in a wet environment, and so it's what we call a wet design cable. Now that generally changes with high voltage cables, 69 kV and above. The general rule of thumb and designs that are implemented would go to a dry type design that has a metallic moisture barrier. Now the design of that moisture barrier has changed over the years and has gone from primarily a lead sheath, an extruded lead sheath, to now there's a lot of copper and aluminum foil laminates and welded designs. But the main point here is that you have a metallic moisture barrier. And we've kind of made the differentiation between those designs for distribution voltage versus high voltage. But if you look at the electrical performance parameters and how the cable has to operate from an electrical standpoint, there's a big overlap between what we do in medium voltage and what we do in high voltage from an electrical standpoint. And again, as we put this entire presentation in the context of cost-effective undergrounding and choices that can be made to make the system more cost-effective yet still reliable, this is an area of overlap that I think that can be explored. And I'll touch on that a little bit more in a little bit as we talk about new materials and new design options that may be out there.
David, so answer this question for the civil engineer is, do I need to specify a different cable if I know that I'm going to be submerged for most of the life of the cable, of my underground distribution cable? For example, I worked at the Hawaiian Electric Company, and everything in downtown Honolulu was basically going to be underwater for its entire life. Did we need to specify a certain kind of cable for that, as opposed to what I might have put in the ground out in the deserts of southern Arizona?
No, not really. And the standards don't really allow for that either. The medium voltage distribution cables that are made today will operate perfectly well in a wet, submersed environment their entire life. There's a lot of cable in cities that you open the manhole and it's wet. It's always wet. There's water in there. You have to pump them before you go in. And that holds true for distribution cable vaults as well as transmission cable vaults. I've been in a number of them when I was working in the construction side of this business. There are a lot of vaults in this country that are full of water all the time.
Yes, there are. Yeah. Okay, good. Thanks for that clarification. I appreciate that.
So what technology does Borealis bring to the table? The insulation materials and semiconducting materials are built on a technology platform that we refer to as BoreLink. It's the name we've given to our technology platform. A number of key performance parameters that differentiate our materials that really lead towards improved processing, faster processing in the cable manufacturing facilities, and at the end of the day, a lower cost product. So what we call classical cross-linking, you have one cross-link bond, which is why we call it cross-link polyethylene. You get a chemical bond between the polyethylene molecules, the ethylene molecules. And so you have one cross-link per peroxide that gets added to the material. So in our technology that we call SuperCure, we've increased the reactivity of the polymer chain. And so you get more than one cross-link for every peroxide that's added to the material. And so what this does is it makes it much more efficient from a cross-linking standpoint, which means you have less peroxide that gets added to the material. So you have less material, which means less byproducts of that cross-linking process. And so if you're familiar with a cable manufacturing, particularly high voltage cable manufacturing, we have to do what's called degassing of the cable after extrusion, which gets rid of these byproducts from that chemical reaction, the cross-linking process. So by having less peroxide in the material to begin with, we have less degassing, which means faster processing time at the cable manufacturer. We have less energy consumption because of the degassing, because it's done in an oven at elevated temperature. So there's a number of benefits here that come in from an energy consumption during manufacturing standpoint, as well as fewer byproducts and faster processing times that lend these materials to benefiting the industry. One of the other benefits, side benefits of this, is it allows much longer extrusion campaigns. For those in the audience that have ever been to a cable manufacturing facility, one of the things they like to do is run their extrusion lines as long as they can before they have to stop and shut down and clean and then restart. And so one of the key benefits here is that you can have much longer extrusion campaigns, make more cable in a single campaign before you have to shut down and clean. Again, it addresses cost effectiveness of these materials and this technology.
And it's more technology that's ultimately reducing the cost of underground.
Yeah, exactly. The picture here on the right-hand side, the example that we're using is a real-world example from one of our customers. They were able to make 30 kilometers of 220 kV cable in one extrusion campaign. And for those, again, familiar with cable manufacturing, that's a pretty monumental achievement to make that much cable in one extrusion campaign. And for submarine cables in particular, where you want to limit the number of joints between these long segments of cable, the longer you can go, the better.
Interesting.
So just a couple examples that I've included in here. The example on the left, and these are cited out of T&D World magazine. This is the Bergen-Linden corridor project that was done in New Jersey. They installed about 23 circuit miles of 345 kV underground cable, XLPE underground cable in northern New Jersey. So again, dense urban area, using cable in areas they're densely populated. The work was all in city streets. And then the example on the right, this is the 500 kV project that Southern California Edison did in Chino Hills, California. Now this is a renewable energy connection. It's not a dense urban area. It's more of a suburban area. Very little work in the streets. It's in right-of-way off the street. And this is a case where EHV underground cable was used because the residents in the area didn't want to see overhead transmission lines. But the time to execute this project was exceedingly long because they first tried to build it overhead and then it ultimately went underground. But this is an example where, again, using EHV, a suburban area, renewables interconnection, so that you can bring those remote sources of electricity that are being built today, in this case, solar and wind, into the load centers.
I think as we spend more money on infrastructure in this country, if we spend $1 trillion on infrastructure for roads and bridges and water and wastewater, we're going to see a lot of relocation of electric transmission lines, and we're probably going to see a lot more undergrounding when we do that relocation. So an example like a public service electric and gas would be a great example. And again, your point's well taken about the 500 kV at Edison, is those people just weren't going to they weren't going to look at it. They fought that thing, and they fought it effectively, where ultimately the regulator said, you got to put that underground. So that was I think that was about 4 miles of 500 kV underground, a fascinating project. And just another reason, at some point in time, some of these projects are going to go underground. Not all of them, but some of them are going to go underground. We've got great industry experience now to point to. And I think we're going to see a lot more of it in the future, especially with the expansion of underground at utilities and the expansion of infrastructure that utilities are going to have to relocate for.
Yeah, and that's an excellent point, and kind of ties back to PDI Squared's mission as well. PDI Squared is trying to build a fact base and advocate for underground where it makes sense, recognizing that it's not everywhere. But there are cases, and Chino Hills is an example, that Ultimately, it was a better project to build underground than overhead because the people just refused to look at it and didn't want those towers in their backyard.
Right. And they were some big towers.
Yeah, they certainly were. I was personally involved in that project. They were some big towers. So HVDC is another technology related to underground transmission. Long distance underground transmission is where this technology is being used. Those following what's happening in Europe are probably familiar with HVDC, the German corridor projects. Again, very long distance transmission from the North Sea on the north coast of Germany, trying to bring all of the offshore wind power down to the population in the industrial centers in the southern part of Germany. So there's going to be huge amounts of cable at 500 kV, 525 kV that get installed in Europe over the next few years as part of these German corridor projects. And there's an announcement a few months ago, a project here in the United States called the So Green Project. Similar concept. You're bringing wind energy from the remote areas in Iowa into the PJM load center just outside Chicago. And then it can tie back into other parts of the PJM system as well. But the point here is it's an underground connection using existing railroad right-of-way to bring renewable energy that is transmission constrained in Iowa and other parts of the Midwest into places like Chicago where the power is needed. And I think it's an excellent use of this type of technology to be able to bring several gigawatts worth of electricity in two cables along an existing right-of-way.
Well, I love this project. I think using existing right-of-ways is a mega trend. You're going to get more ampacity out of existing right-of-ways. And I think when I wrote that paper back in 2012, I was thinking of transmission right-of-ways and not transportation right-of-ways. But what So Green is it's using railroad right-of-way, so they basically don't have to go and route and permit the project. So we do a great job as an industry in designing and building transmission lines, but the routing and the permitting is what takes years and years. And so the developers of So Green have basically said, okay, we're going to eliminate that as a challenge, and we're going to make it HVDC, and we're going to put it underground. And so congrats to PDI Squared member Prysmian and also to Borealis for, I'm going to assume that you're providing the polyethylene for that Prysmian cable. Mm-hmm. And that's a very exciting project.
Yeah, and there's other similar projects being proposed in the U.S. There have been other ones very close to becoming reality over the years, and they just haven't been able to get across the hurdle. But we're hoping, obviously, that So Green kind of opens the door for other opportunities in HVDC. If you're not aware, there are two other extruded HVDC projects in the U.S. This is a world map and different HVDC projects that have taken place around the world, all of which have Borealis material in them, I might add. But the Trans Bay project out in California and the Cross Sound cable in Long Island have been giving reliable performance for decades now. And so while it's not commonplace yet in the U.S., it's not exactly brand new either. The technology has been around. As an organization, we have thousands and thousands of kilometers of cable in service around the world at a number of different voltage levels. So we're excited about the future of HVDC and the part it can play in the renewables growth here in the U.S. Because again, you're not going to build a wind farm just outside New York City or just outside Chicago. They're going to be built in places that are remote from where the load centers are, and you have to build transmission infrastructure to get those megawatts to market.
I think this map, David, shows us that there is HVDC all over the world, and I'll just put a plug in for Seagray right now. The Seagray group is basically advocates for high voltage transmission. They're probably the de facto source of technical expertise on transmission-related projects around the world. And so if you're interested in HVDC and you want to know more, there's somebody at Seagray probably on the U.S. committee, or certainly on the U.S. committee, that can direct you to some expert in the world that can help you and talk to you about some of these projects. So you don't know about that sometimes if you don't get outside of the U.S., but Seagray certainly gives you an opportunity to do that and learn more about some of these projects that in other countries and other utilities that are having success with it.
Yeah, absolutely. Seagray's a great organization. I was the U.S. rep to Seagray Study Committee B1 for 6 years, so I'm very familiar with Seagray and the work that they're doing. So the last topic I want to talk about, and we'll shift gears here just a little bit, to a material that we offer that's being used primarily in Europe at the moment, but I want to mention it here and make the audience aware of it, and that is copolymer water tree retardant crosslink polyethylene. Earlier, we talked about a kind of a different version of water tree retardant materials that are used in distribution cable, have been used in distribution cable here in the U.S. for many, many years. And it's one type of material science that gets used to make those cables. The copolymer water tree retardant materials is a different material science that's been used in Europe for a number of years now, very reliably. And one of the unique things about the material that we offer, it's being used with great success in submarine collection system cables for offshore wind. It started out at 33 kV, and as the turbines have gotten bigger, we're now at 69 kV, or they use 66 kV offshore wind collection system cables in Europe. And so these are wet design. I mentioned earlier wet versus dry design cables. And so this is an example where at the 69 kV voltage level, we're using a wet design water tree retardant material in a submarine cable in salt water, and it performs exceedingly well and is very reliable. So you've got a case here where we're taking a water tree retardant material and using it in a 69 kV cable. It passes 2-year wet electrical aging requirements in Europe, whereas in the States we only have a 1-year wet electrical requirement. So a 2-year wet aging in salt water at what we term a transmission voltage level. And so I think this, again, is a materials choice and an option that's available to the industry that can offer benefits for cables that need to operate at higher voltage levels in wet environments. And it would make the cable design cheaper. You can eliminate the metallic moisture barriers and open the door to other possibilities.
Good.
So my last slide, kind of tongue-in-cheek, we kind of laugh that the utility industry in the United States is always in a race to be second. And having worked in R&D and development at different companies over the years, it's a little tongue-in-cheek, but just because we haven't done it before doesn't mean it doesn't work. I think there's a lot of good technology and opportunities out there that, as we talk about, can help make the underground system more cost-effective.
Well, good. Thank you, David. I appreciate that. And I think what we'll do now is we will answer some questions from the audience. We've got a little bit of time left here, about 15 minutes or so. So appreciate some of the questions that have come in so far. And David, we'll get straight to those. And I encourage you to send some more in if you got them. Okay, so somebody said, so I got a question here. What's the shelf life of cross-linked polyethylene raw material, which I guess that means the polyethylene? What's the shelf life? Is that really applicable to something that people need to know, or are they asking more about, how long can the cable sit on a reel before it gets put out into the field? You have a feel for maybe where that question's coming from?
Well, yeah, there's two things there. One is the shelf life of like the material that we would sell to a cable manufacturer, and we specify and clarify those issues with our customers, and it's found in our product specifications and materials that we provide to our customers. Generally, I'm not going to give any specifics here, but generally would range between 18 to 24 months, depending on the exact product that we're talking about, and different exact grades of material can have a different shelf life, but you're generally in that 18 to 24 month range.
Okay.
And then once the cable is manufactured, obviously there is no real shelf life per se. I mean, whether the cable's sitting on the reel or in service in the ground, it's going to last for 40 plus years.
Okay. Had a question here about how do you measure the contaminants? So you had a slide that talked about the contaminants that might be in the manufacturing process. How are those contaminants measured? And I think this question was, what's the unit of measure, parts per million, or was there some unit of measure?
Yeah, so the industry standards give you the requirements on particle size and a number of hits that you can have within a certain kilogram of material. And different voltage classes have different requirements. So again, as you go up in voltage class of material, the contaminant size requirement gets smaller, and the number of hits that you get for that size gets lower. We use pellet inspection technologies in our plant to optically look at the individual pellets, and it's digitized and computerized so that the computers are finding these contaminants and imperfections and can kick out the information. And if we exceed certain thresholds, the material gets quarantined and additional investigation happens.
Okay. Next question. This question comes from a utility. Does supercure result in more cross-link sites than conventional cure?
So the answer to that is no. Doesn't result in more cross-link sites. What it does is offer more efficient cross-linking, and we can do it with less peroxide added to the material. So that when we make the polyethylene pellet, before we add peroxide, it's not going to cross-link, right? So we add peroxide to the pellets that will help initiate that cross-linking process. And because of the supercure technology that we've implemented in the polymer itself, we don't need as much peroxide. So there's less peroxide, which means less cross-linking byproducts, which means less degassing and faster cable manufacturing. Less time in the degassing ovens to achieve the same level of degas.
Okay. I'm going to ask another question from the same utility out west. Thanks for the questions, by the way. Are the losses higher for copolymer WTR, all in caps, than standard crosslink polyethylene?
I assume we're talking about electrical losses here. I'll make that assumption. And the answer is no. They're very, very similar. I don't think you would ever notice a difference, and they are much lower than EPR.
Okay.
Ethylene propylene rubber, yeah.
Somebody had a question about the Champlain Hudson Power Express HVDC project. It wasn't a question as much as it was a statement that, hey, there's another big DC project going on. Are you aware of this HVDC project, the Champlain Hudson Power Express?
Oh yeah, very aware of that project. Yeah, I've lived that one as well, and with a previous employer. Yeah, so yeah, we're very familiar with Champlain Hudson, and certainly hopeful that it makes it across the finish line.
Yeah, that is.
And now, just for those who aren't familiar with the project, it's a connection that's been proposed from Canada, from Hydro-Quebec, down into New York City. And the idea is that, again, it's renewable energy, in this case, hydroelectric. So clean energy from Canada, this time down into New York City, and you're delivering a couple gigawatts worth of electricity on two cables over a very long distance, yeah.
Yeah, there's a few other projects that want to do the same thing. I think Northern Pass up there at Eversource Energy was a great project, bringing Hydro-Quebec hydropower basically down to the load centers of the East Coast.
Yeah, there have been a number of projects proposed, all with the same general concept of bringing hydro from Canada down into the New England Northeast area, be it Boston or New York City or other locations up in the Northeast. But again, nothing's been built yet. They become a little more complicated when you get into international trade of electricity, that those projects have to be approved at the presidential level. So politics get involved, and for a number of different reasons, none of those have
Sure.
materialized yet.
Yep. Okay, I'm going to ask this question from a utility on the East Coast, and I think you're going to be able to answer it. I'm just going to read it directly. Are your voltage ratings phase-to-phase or phase-to-ground? For Delta systems, I have a phase-to-ground fault. The voltage on the unfaulted conductors can go up to 133%. Should I go with a higher voltage rated cable, for example, 133% higher on Delta undergrounded systems? Does that help? Does that, you know where that's coming from?
Yeah, I think I understand the question. I will say all of the voltage ratings that I've discussed today are all phase-to-phase, which is how cables are rated. We follow the general IEC and IEEE guidelines on how to discuss and talk about voltage classes and voltage ratings of equipment. Now, that said, I'm not a double E. I'm not going to attempt to answer around faulted conductors and voltage rise for this type of question without more information. So I guess I'll leave it at that. Okay.
No, that's good. Thanks for taking a stab at that. Okay, here's a question that's a burning question, I can tell from this gentleman. He had some cross-linked polyethylene that turned color after 30 years of operation. So would you expect that a cross-linked polyethylene cable could potentially turn color after a few decades of operation?
The first question I would ask him is, what's the thermal history? One of the things you will see with cables that have been overheated is that it can result in changing color of the material. So without a good handle on the thermal history of the cable, it's hard to tell. But that's one of the things that can happen when cables have been overheated and run at too high a temperature for long periods of time.
Yeah, I think that sounds like somebody needs to get INCOR in there and take a look at that cable and figure out what the cable is.
Yeah.
Okay, here's the last question we have from the audience, and thank you for sending in all these questions. We appreciate it. What is the predominant design in offshore wind farm array cables, wet or dry?
Great question. It has changed over the years. When offshore wind began, you had a lot of dry design cables with metallic moisture barriers, in particular lead sheath on them. As offshore wind in Europe has become more and more prevalent, and they've tried to drive the cost out of those systems, they have transitioned to wet design cables. So the cables being used today predominantly are wet design, and that is true even with the voltage levels going up from 33 kV to 66 kV, as I mentioned, with the turbines getting bigger. The other thing about using a wet design without the metallic moisture barriers in there is it lends the design much more favorably to dynamic rating that are going to be needed for floating wind turbines. You know, in the U.S., we're at the very beginning stages of offshore wind. We're talking about fixed platform turbines right now. But particularly on the West Coast, and as you get farther and farther offshore, the discussion starts to move to floating wind turbines. And one of the challenges there is that as the turbine floats, the cable connected to the turbine then becomes dynamic. It has to move, right? As the thing floats up and down, the cable has to move. And so if you have lead sheath and other types of metallic moisture barriers in your cable, now you've got a fatigue issue that has to be dealt with. And so by going to wet design cables, they work extremely well in these dynamic situations. So again, there's a number of reasons why they've moved from dry to wet, but the kind of the trend and what we've seen in Europe and what's being installed today is a wet design 66 kV inner array.
Interesting things that we're all going to get to learn as we build offshore wind here in this country, for sure.
Yeah, absolutely.
Well, David Lindsay from the Borealis Group, thank you very much. I'll just say, if you've got any kind of concluding remarks, give us your conclusions, and we'll wrap it up. I think we've got all the questions answered from our audience, and appreciate what you had to say today. What's your final message to everybody today?
Yeah, thanks, Mike. I appreciate everybody's time. I appreciate everybody staying with us for the hour today. Borealis is certainly a leader in this technology and offers materials that we think can provide very reliable cable service for the 40-plus expected years of life. My contact information is on the screen there. Take a minute to jot it down. I'd be happy to talk to anybody one-on-one and answer any questions that you have, and look forward to getting back to seeing people in person as soon as possible.
Boy, I agree with that. Well, thank you very much. And on behalf of Borealis Group and David Lindsay and the Power Delivery Intelligence Initiative, we just want to tell you thank you very much. This was number 5 in a series of 6 on the 21st century cost of underground. And join us in late August, for our final webinar in the series of 6. It'll be G&W and Southwire, and we will look forward to having you join us then. In the meantime, have a great day and be safe. Thank you for joining us.